Hello, my name is Erin Bugby, and I'm a PhD student at Carnegie Mellon University. This is a pre-recorded presentation for the 2022 International Conference on Cognitive Modeling. The title of this talk is Leveraging Cognitive Models for the Wisdom of Crowds in Sequential Decision Tasks. Many decisions people face are sequential in nature. Alternatives emerge and are considered consecutively over time. Imagine, for example, that you are considering renting an apartment in New York City. Your goal is to select the best apartment available. In such a dynamic market, it is not possible to compare all options before making a selection. Instead, you need to decide instantly whether you take the current apartment or forgo it, in which case it is very likely that you would not be able to go back to that option. The more apartments you see, the more informed your decision will be. However, this creates a problem, as you cannot see many apartments without risking losing the best one in the set. The question is, when do you stop visiting apartments to maximize your chances of getting the best apartment in the sequence? The literature on sequential decision-making has emphasized that people are often suboptimal when deciding when to stop searching. These problems are particularly difficult because they require considering past, current, and future options, as well as making trade-offs of risk and uncertainty. Recently, Thomas et al. Has proposed using the wisdom of crowds as a way to address these difficulties in sequential decision-making problems. This involves aggregating individual decisions to make a crowd decision in the hopes that the crowd will be wiser than any one individual alone. In this research, we build on the work of Thomas et al. 2021 to test the benefits of the wisdom of crowds using cognitive models. We rely on two known sequential decision tasks and their previously collected datasets from Guan 2019 and Guan et al. 2020. Further, we utilize two existing cognitive models of sequential decisions in these tasks. In contrast to the work of Thomas et al., these cognitive models are generative process models that learn through experience to produce predictions of human stopping decisions in the absence of human data. These models act based on a theory of decisions from experience, instance-based learning theory, and we show that they are able to replicate human sequential decisions closely at both an individual and crowd level. In this presentation, I will describe the two tasks and corresponding datasets we leveraged from Guan et al. 2019 and 2020. I will then present instance-based learning theory and the IBL models we use for each task. I will detail the model simulation and wisdom of crowds aggregation methods, building off of the work of Thomas et al. 2021. I will then present the individual and crowd results for both tasks, and finally, I will conclude with a discussion of the results and implications. I will first describe the experimental tasks and data sets that we focus on in this paper. The first task we use is the balloon analog risk task, or the BART. In the version of the BART we use from Guan et al. 2020, participants are presented with balloons that start with a value of $1. They are instructed that they can either pump or bank on each decision. If they pump, the value of the balloon may increase by $1. However, there is some probability that the balloon will burst. If they bank, they will collect the monetary value of the balloon, and this amount will be added to the overall bank. The goal is to maximize the total monetary reward over many problems. On the right are screenshots of the tasks from Guan et al. 2019. In this dataset, there are 56 participants. There are two conditions in which the probability of the balloon bursting was varied to be a constant 0.1 or 0.2. The design was within subjects, so every participant completed 50 problems in each condition in a random order. The second task we focus on is called the optimal stopping task. In the optimal stopping task, participants are presented with sequences of cats and their corresponding weights. They are instructed to choose the cat in the sequence with the highest weight, where weights range between 0 and 100 pounds. On each cat, the participant decides whether to select it, indicating that they think it weighs the most in the sequence, or to pass and move on to the next cat. Once a selection is made, no information is provided about unseen cats. If the last cat in the sequence is reached, it must be selected. Participants are provided feedback on the correctness of the decision and are rewarded only for choosing the cat with the highest weight. The dataset consists of the same 56 participants who completed the BART. There are 4 conditions. The distribution of weights was manipulated to be either uniformly distributed, called neutral, or beta distributed, called plentiful, since weights are skewed towards higher weights. The length of the sequence was also varied to consist of 4 or 8 cats. The design was again within subjects, with every participant completing 40 problems in each condition, and both the problems and conditions were presented in a random order. The idea of the wisdom of crowds is that we can consider the behavior of many individuals with the hopes of making a wiser decision as a crowd than by choosing according to any individual alone. In this paper, we focus on the crowd deciding according to the behavior-based majority decision. That is, at every choice, the crowd decides to act in alignment with the majority of participants. In the BART, this means the individuals choose to either pump or bank on each trial, and the crowd chooses to do what the majority did. It is assumed that once an individual banks, they would have decided to bank on all future decisions. For the optimal stopping task, the individuals choose to select or pass each alternative, and the crowd decides in alignment with the majority out of those who have not already made a selection. Now that I have introduced the tasks in the datasets, as well as the wisdom of the crowds methods, I will summarize instance-based learning theory. Instance-based learning theory underlies the 2 cognitive models that we use for these tasks. The 2 cognitive models that we use in this paper are both based on instance-based learning theory from Gonzalez et al. 2003. Instance-based learning theory incorporates some of the cognitive and memory mechanisms of the well-known ACT-R cognitive architecture. Generally, learning occurs by interacting with the environment and receiving feedback, and then instances are accumulated and stored in memory to be retrieved for future decisions. Instances are memory units that consist of 3 elements: the situation or the contextual features, the decision being made, and the utility or feedback received from the decision. Instance-based learning theory proposes that the decision-making process consists of 3 main components. The first is the activation of instances. Each instance in memory has an activation value, which is dependent on recency, frequency, and similarity to the current situation. The activation of an instance determines the probability of retrieving it according to the softmax equation. And a blended value is then calculated for each action through a mechanism called blending. This is calculated as the sum of the probability of retrieval multiplied by the outcome for each instance. Then ultimately, the agent selects the action with the highest blended value greedily. Here I provide the mathematical equations for instance-based learning theory. Feel free to pause the presentation here to review them. Using instance-based learning theory, we can develop cognitive models called instance-based learning models, or IBL models. These are built using Pibble, a Python implementation of IBLT. For this work, we use 2 previously developed IBL models from Bugbee and Gonzalez. The first is that of the BART. For this model, the instance structure consists of the situation, which is the number of pumps of the balloon, the decision to pump or bank, and the utility. The utility depends on the status of the balloon. It is 0 if the balloon bursts, otherwise it is the value of the balloon, which is the starting value of 1 plus the number of pumps. The model of the optimal stopping task is very similar. The situation consists of the value of the current alternative and the number of alternatives remaining in the sequence. The decision is to select or pass, and the utility is 1 if the selected alternative is the maximum in the sequence and 0 otherwise. Using these IBL models, we can simulate choices for individuals making decisions in the BART and optimal stopping task. Each IBL model agent is presented with the same stimuli in the same order as a corresponding human participant. That is, we have 56 human participants and 56 IBL model agents, so there's a 1-to-1 mapping. We use for both IBL models the default parameter values for decay and noise. I will now present the results of the human participants alongside the predictions of the IBL model agents. I will present both on the individual and crowd level. We'll start with the results of the BART. These figures show the distribution of mean rewards for human participants on the left and IBL model agents on the right. The figures also show the optimal reward as the red circle, and the reward of the model crowd from Thomas et al. 2021 as the blue square. The green triangles show the crowd behavior, and the dashed lines show the average behavior. The distribution of mean rewards is slightly lower for the IBL model than for humans. This is explained by the need for the IBL model to learn from experience how to gain points without reading instructions as humans do. The crowd behavior is comparable for the human and IBL model in both conditions. We see that the crowd performs better than the average across participants in both conditions for the human and IBL models. These results indicate that the crowd performs this task better than the average individual, and the IBL crowd behavior closely replicates the human crowd. These figures show an example of the behavior of humans on the top and IBL agents on the bottom for one problem. In this particular problem, the balloon bursts at pump 15. We observe comparable pumping behavior for the humans and IBL agents. We see more IBL agents pumping more, but we also observe that for the crowd behavior, the human crowd banks at pump 4 and the IBL model crowd banks at pump 3. We will now move on to the results of the optimal stopping task. These figures show the accuracy distributions for humans and IBL model agents in the 4 conditions of the optimal stopping task. We again have the optimal accuracy, that of the Thomas et al. Model crowd, and the accuracy of the human and IBL crowd, as well as the average accuracy. We see that the performance of the IBL agents is similar to that of the humans, and that the crowd behavior is also comparable. Again, the crowd behavior is better than the average participant, and the IBL crowd closely replicates the human crowd. This figure shows the stopping probabilities in the optimal stopping task at each position in the sequence for each condition. The solid lines correspond to a particular individual's stopping probabilities over all problems. The dashed lines correspond to the stopping probabilities of the crowd. The similarities of the IBL agents to the human participants, as well as the IBL crowd and the human crowd, indicate that the IBL model is able to capture the stopping probability of human participants under each condition, and that the IBL model is able to replicate the human crowd closely. In this research, we investigate the power of the wisdom of crowds for sequential decision-making. We build on the work of Thomas et al. 2021 by demonstrating how cognitive models can be used to simulate a crowd of agents that behaves like a human crowd. We use cognitive learning models, IBL models, which are based on a cognitive theory of decisions from experience. We show that these models can produce choices in alignment with humans at both the individual and crowd level. This is an advancement upon the descriptive models of Thomas et al., as these models learn from experience and can make accurate predictions without fitting to data. In conclusion, our results demonstrate that the cognitive models we have previously developed can learn to perform as human participants in sequential decision tasks. And we show that the crowds of IBL agents behave similarly to those of human participants. In future work, these models can be applied to settings in which human adaptation is a prominent feature of the task. Here are the references from this talk. Please refer to the paper for a full list of references. This paper was co-authored by Chase McDonald and Cody Gonzalez. Thank you for watching this talk. Please feel free to reach out with any questions or comments regarding this work.